Hello, today we're going to be talking about pneumatic power, and pneumatic means gases, so primarily we're talking about air. So those are some things that we're going to be coming through. So pneumatics is the use of gas, usually air, flowing under pressure to transmit power from one location to another. Gas in a pneumatic system behaves like a spring since it is compressible. So compressible means that you can squish it. So if I had a sealed syringe with air in it, I could squish that syringe and make it go down, and then when I let go of it, it would spring back to where it was originally. So gases behave like springs. So pneumatic systems use a compressible gas, okay, meaning basically a gas. They tend to be jerkier, quicker, jumpier motion than hydraulics, which use liquids. They're not as precise because they are jumpier. They require lubricant, so usually there's some air in there's some oil in the airline. They're cleaner than hydraulic systems since hydraulic systems tend to leak oil. They often operate around 100 psi, and they don't produce as much power as hydraulic systems. So early pneumatic uses. So here we've got a bellows. Basically, it was used to blow air into the coal fires of blacksmiths. They were back in, I don't know when this was, in the 1700s, 1800s. Otto von Guericke showed that if he took the air out, he made vacuum pumps. And he showed that if he took the air out of the sphere, which had two halves, it was in Magdeburg. They were called the Magdeburg sphere. If they took the air out of these two, sealed this thing together and took the air out, that two teams of horses can pull it apart to show how strong his pumps were. Here's a subway that ran on air power. So kind of interesting. Completed in 1817. Only 312 feet long, and only ran for 3 years. So when we're talking about a gas and we're trying to define what our system is, there's three main variables. That's pressure, temperature, and volume. Those are the big variables that we're going to be talking about. Gases have no definite volume, which means you can squish them. Gases are highly compressible, which again means you can squish them. And gases are lighter than liquids. Duh. Okay, air is lighter than water, that kind of thing. So there's three basic gas laws that we're going to be looking at today: Boyle's law, Charles' law, and Gay-Lussac's law. So before we do that, we're going to talk a little bit about temperature and pressure. Can it get colder than 0 degrees Fahrenheit? Is that possible? Yes. Can it get colder than 0 degrees Celsius? Yes. Can it get colder than 0 Kelvin? No. Okay. The colder the atoms get, the slower they move. And there's a point at which atoms can't move any slower, and that's when they're stopped. Okay. So 0 Kelvin is the temperature at which atoms stop moving. And so Kelvin is the absolute zero. So 0 is the coldest it can get. 0 Kelvin is the absolute scale in the metric system. In the English system, we use Rankine, so 0 degrees Fahrenheit is actually 460 degrees Rankine, that kind of thing. So 0 degrees Fahrenheit is not true absolute zero. Absolute zero is minus 460 degrees Fahrenheit. We measure the absolute temperature in degrees Rankine. So to convert between Fahrenheit and Rankine, okay, all you do is take your Fahrenheit temperature and add 460 degrees to it. That's it. Okay, so if the temperature is 65 degrees Fahrenheit, what's the temperature in absolute in Rankine? Add 460 to get that, 525 degrees Rankine. So that's no big deal. This is kind of where we're at with the temperature conversions in your equations. So under 9, these are how to convert different temperatures between one and another. So be aware that those are available to you. Okay, and a little bit on pressure before we get into the actual gas laws. So here we've got a pressure gauge. This reads pressure in PSI, pounds per square inch. This is a very common device in manufacturing settings, things like that. Is there any pressure on the pressure gauge right now? Well, sure there is. There's atmospheric pressure, the pressure from the air around us. So why does it read 0? Well, there's what's called gauge pressure. Okay, gauge pressure reads how much pressure there is greater than atmospheric pressure. So if a pressure gauge reads 0, the pressure is really 14.7 psi on it. That's atmospheric pressure, is 14.7 psi. This one actually goes below. It reads a vacuum. We don't have to worry about that, but that shows that you can actually go below 0. And it's, in actual pressure. So really this is pretty super easy to get between gauge pressure, and gauge pressure is basically just what a gauge reads. You add atmospheric pressure to it. So we're always going to deal with PSI. So you're always just going to add 14.7 PSI to the gauge pressure to get to absolute pressure. So take your gauge pressure, add 14.7 psi, and you're done. Okay, just like add 460 degrees to get from Fahrenheit to Rankine, and you're done. So there is a, it says that right here, absolute pressure equals gauge pressure plus atmospheric pressure, not absolute. We've got absolute and atmospheric, so it can be a little confusing. If I were you, what I would do is on my equation sheet, I would make a note on there that, and just write it P absolute equals P gauge plus 14.7 psi, and just make a little note right there, because it doesn't tell you that atmospheric pressure is 14.7 psi. So these are the equations that we're going to be getting through this unit, fluid mechanics. We're going to start with these first 4 in this PowerPoint, and then we'll get through the other 3 later on. So absolute pressure, as we measure pressure in PSI. If a gauge reads 120 PSI, what's the absolute pressure? So we're given gauge pressure. So to convert from gauge pressure to absolute pressure, all you do is add 14.7 PSI. Okay, so 134.7 pounds per square inch. So PSI, pounds per square inch, this is just another way of writing that. Okay, so we're going to get into gas laws. The first one that we deal with is Pascal's law. Pressure equals force over area. So P equals F over A, and again we're getting into those equations that are in 9.16 through 9.22. Pressure, P is pressure, and they have a capital P here and a lowercase p here, don't ask me why. F is force, and A is area, so pressure equals force over area. So it's a pretty simple equation, P equals F over A. So again, showing you that's that equation right there. So here's an application of that equation. How much pressure can be produced with a 3-inch diameter cylinder and 50 pounds of force? So we've got the force. Okay, we're looking for pressure, which means we need the area. Now the area that we're talking about is this cross-sectional area. Is the area of the piston. We've got a diameter of 3 inches. So how would I go from diameter to area of a piston? Well, it's a circle. Okay, so we're talking about the area of a circle, which is pi r squared. Now notice that's radius squared, pi r squared, and this is given as diameter. So I've got to have that squared. So pi times 1.5 squared. It gives me an area of 7.1 inches. Okay, so now I've got the area. The next step is to use my equation. P equals F over A. Okay. Pressure equals force over area, and that should be capitalized, I believe. but it doesn't really matter. So, so the the force that we're dealing with is 50 pounds. The area we just calculated was 7.1 inches squared. Okay, do the division, and you get 7.1 pounds per inch squared. Okay, pounds per square inch, or PSI. Always feel free to pause if you need to look at this a little bit longer than the time that I spend on it. I tend to go through this fairly quickly, I think, but it might take you might need to pause it a little bit and process a little bit more. Okay, on to gas laws, the other gas laws anyway. So we've got Boyle's law. Boyle's law basically says that if you decrease the volume, the pressure is going to go up. So in other words, if you squish something, okay, its pressure is going to increase. So if you were to take an empty water bottle and fill it with air, seal it off, and you were to squish on the sides of it with your hand, and you were to decrease the volume of that water bottle, the pressure inside would go up. That's what Boyle's law says. Okay, the key thing to note here, that pressures need to be absolute pressure. So if we're given gauge pressure, we've got to convert to absolute pressure. So and this is Boyle's law here. Your P1V1 equals P2V2. The ones mean your initial, so this is your initial pressure times your initial volume equals your final pressure times your final volume. So you're going to have your before and after picture, basically, is how that works. So before and after. So these are the gas laws that we're going through right now. So this is Boyle's law right here. P1V1 equals P2V2. Again, they've got that uncapitalized. I wonder, absolute pressure P. Oh, they're using big P as power. Okay, so that's intentional. Okay. So we've got a cylinder filled with 40 cubic inches of air at a gauge pressure of 60 psi. The cylinder is compressed to 10 inches cubed. What is the resulting absolute pressure? Okay, so P1V1, so we squish it. What happens to the pressure? Well, we know the pressure is going to go up. At least it should. If it doesn't, we done messed up. So we've got our initial pressure is 60 psi. Okay, our initial volume is 40 inches cubed. Our final volume is 10 inches cubed. What is the final pressure? Now the first thing we need to do is it says 40 inches cubed at a gauge pressure of 60 psi. So we've got to convert that gauge pressure into absolute pressure. So by adding 14.7 psi, we get 74.7 psi. Then we plug into the formula. Okay, so this kind of gets a little bit messy here, but so P1, which is 74.7, times V1, which is 40 inches cubed, okay, equals P2, which is what I'm looking for, times 10 inches cubed. So multiply the 74.7 times the 40, okay, and then divide by the 10 inches, and we get 300 pounds per square inch. So that is an example of Boyle's law. Again, you know, I think the equation is pretty straightforward. P1V1 equals P2V2. Just make sure that you convert gauge pressure into absolute pressure before you plug it into that equation. And then we've got Charles' law. Charles' law is that if you increase the temperature of something, its volume will increase. So if you heat something up, it's going to get bigger, is basically what Charles' law says. So if you were to take a balloon, a dark black balloon, and leave it out in the sun, okay, it's going to warm up and that balloon's going to expand, okay, assuming that we're at a constant pressure. So Charles' law is V1 over T1 equals V2 over T2. So it looks a little different than Boyle's law. And the key thing here is that the temperature needs to be in Rankine. Okay, we've got to convert to absolute temperature. We've got to convert to Rankine. Okay, So here we've got an expandable container filled with 28 cubic inches. Now you guys got to realize that 28 cubic inches, that cubic inches means that's volume. Okay, so you gotta make that connection. It's at 32 degrees Fahrenheit. Okay, the container is removed from the icy water and then heated to 200 degrees Fahrenheit. What's the resulting volume? Okay, so we take that out and it expands. Oh, look at that, it even. Does it expand? Oh, it does. Look at that. It expands. Woo! Check out that animation. So, alright. So the first thing we need to do is, we'll list what's known and what we want to know. We've got V1 is my volume, my initial volume. V2 is what we're trying to find. Okay. T1 is 32 degrees Fahrenheit. That's my initial temperature. And my T2 is 200 degrees Fahrenheit. And that's my final temperature. The first thing I need to do is convert the temperatures in Fahrenheit to Rankine by adding 460 degrees, so that's easy peasy. So we get that T1 equals 492 degrees Rankine, and T2 is the bigger temperature, it's 660 degrees Rankine. Okay. The next thing we're going to do is we're going to plug into Charles' law formula. So V1, which is 28, divided by T1, which is 492 Rankine, equals V2 over 660, which is my T2, okay? And then basically we're going to take 28 divided by 492, and we need to multiply we need to multiply by 660 to solve this equation, because 660 is down below. Okay, so you need to multiply both sides by 660 and get what you get. You get 38 cubic inches. Then we'll check and make sure it makes sense. Did my volume go up? It did. So that at least makes sense, that my volume went up from 28 to 38 cubic inches. That seems reasonable. Okay, and the last one, which is Gay-Lussac's law. Basically, what Gay-Lussac's law says, that if you increase the temperature, the pressure is going to go up. So if you heat, assuming that the volume is constant, so in a rigid container. So if you heat a rigid container, like a can of spray paint, you throw it in a fire, okay, the pressure inside that's going to build. Okay, we know this. If you take a rigid container that has a constant volume, more or less, throw it in a fire, the pressure is going to build, okay, until the container can no longer hold it, and in which case the volume is going to go up at that point, because it's going to rupture. And when you're using Gay-Lussac's law, pressure and temperature must all be absolute. Okay, so you heat something up, the pressure goes up. Okay, so Gay-Lussac's law is P1 over T1 equals P2 over T2. And again, you don't need to memorize these equations. Obviously, you've got your equation sheet always available to you. So here we got, again, these require a little bit more work because we got to convert everything. We got to convert pressures and temperatures. So we've got a 300 cubic inch sealed container sitting outside. In the morning, the temperature inside the tank is 62 degrees Fahrenheit, and the pressure gauge reads 120 psi. By afternoon, the temperature is expected to be 90 degrees Fahrenheit. What would the temperature be at that point? So again, trying to figure out what equation you're supposed to use. Here it's simple because we just gave you the law, and you know we're going to be using the equation that goes with that law. But if you label what's what, they give you the volume here, and the volume doesn't affect anything. So it gives you the initial volume, and then it doesn't say anything about that. It gives you, here's my initial temperature, okay, here's my initial pressure, okay, here's my final temperature, okay, what is the final pressure? So so we got to keep track of what it is we know and what we're trying to find, and that'll help you figure out which equation that you're supposed to use. So what we need to do is convert our pressures and our temperatures. So we'll start out with our pressure. So add 14.7 psi, and again, write that down on your equation sheet so that you don't have to remember that. Although if you do it a few times, it'll probably sink in anyway. Okay, and then we need to convert our temperatures by adding 460 degrees Fahrenheit to them to get them into Rankine. And then we use our equation. Okay, so P1, which is our gauge, our absolute pressure, divided by our temperature equals P2 over T2. So now, if we do this right, we know our temperature should go up a little bit because the temperature goes up a little bit. So let's get our final answer, and we get 140 psi. So it goes from 134.7 to 140 psi. That makes sense because it only goes from 522 Rankine to 550 degrees Rankine, so it's not a huge temperature increase. It's not a huge pressure increase, but the pressure does go up. Okay, so that's it for the math. So this is what this is kind of an old looking compressor, but this is what a pneumatic system might look like. So here we've got a pump, okay, which is compressing air. Okay, it's storing air inside a tank. Okay, the tank is pressurized. It has to be. So here's how the compressed air gets to various other things. So the transmission line's usually a pipe. Okay, well here's our compressor finally showed up. Cylinder, I don't know what that cylinder is doing. Usually it goes through an air filter to filter out any particles that might have gotten trapped in there, maybe some rust from the pipes, and then a regulator which regulates the pressure down from usually 100, 120 psi, something like that, down to whatever psi you need at your operating station. What ends up happening is after you compress the air, and then it warms up and then it cools, there tends to be a little bit of water that will condense, and you need to drain that off because it's not good for the steel tanks and things like that. So you've got drains that drain that off. This picture's not really that clear. I don't quite get that. A pressure relief valve. So they've got a pressure in case something bad happens, something like the compressor doesn't shut off. You've got a relief valve that bleeds off pressure at a certain pressure. It'll blow off air. So to keep the pressure from building up too high. These are things that you might see on your or should see on your device. Some of these things. Different types of pumps that would compress air, and sometimes oils and things like that. Reciprocating reciprocating piston. So this thing spins around, and then these pumps work kind of like a car engine, in kind of in reverse, to pressurize air. Here's a rotary screw. I haven't seen too many of these. So these screws rotate and compress the air or the fluid. Here's a rotary vane. So this thing spins around, and these vanes extend and retract to get the air or fluid compressed. So anyway, and that is that. Thanks for sticking with me, and let me know if you have any questions.